This video focuses on qualitative imaging methods, which are vital for understanding anomalies, boundaries, and other key qualitative features within tissues, especially in medical diagnostics like brain imaging. Instead of providing precise material properties, qualitative approaches identify areas of interest based on differences in dielectric properties. The confocal imaging process, depicted on the left, forms the backbone of these methods. This approach simplifies solving the inverse scattering problem by treating each scatterer, such as a tumor or stroke, as an electromagnetic point source. Regarding the multistatic and near-field imaging characteristics of the imaging setup, to reconstruct an image we need to apply a focused beamforming algorithm such as confocal beamforming algorithm. For this, the first step is identifying focal points to calculate energy pattern of the reflected signal at these points, which for multistatic imaging algorithm, will be done by coherence signal integration. Radar-based imaging techniques need prior information about the effective permittivity value of the medium. This value is usually set based on the average permittivity of tissues at midpoint frequency. However, in clinical application, the average effective permittivity may be variant in different individuals who have different body shapes and habitus. Hence, effective permittivity estimation technique is usually needed to estimate the overall effective permittivity of the medium prior to imaging. This slide explains a microwave imaging system designed to analyze and reconstruct images of internal structures, such as biological tissues. The diagram on the top left shows the microwave imaging system overview, including an antenna array surrounding a tissue sample, likely biological. The antennas emit microwave signals, which pass through the tissue and are scattered. The tissue under investigation scatters the microwaves, creating an electromagnetic response. The scattered microwave signals are collected by the antennas and fed into microwave electronics for processing. The switching interface selects the active antennas at each moment, and data is transferred to a computer for further analysis. This setup represents the real-world implementation of microwave imaging, where signals interact with tissue to provide information about its internal structure. In addition, at the bottom, the equivalent electromagnetic source model of the system is demonstrated, which is the basic assumption of the qualitative imaging system. The figure represents wave propagation from the source to the tissue, back to the receiver. The blue dashed lines represent the wave interaction with internal structures, which scatter the signal. The scattered fields are used to backproject an image of the tissue's internal structure. This process iteratively reconstructs an image by combining data from multiple antennas. Signals from multiple sources are represented as time-domain waveforms. These signals correspond to the scattered field measured by different antennas. The signals are time-shifted and summed. This time-shifting process adjusts the signals to align with the delay caused by the signal's interaction with different parts of the tissue. Once aligned, the signals are summed and processed to extract useful features from the measurements. Finally, the processed signals are used to form an image, showing the internal structure of the tissue, with color-coded intensities that represent different tissue properties, e.g., permittivity, conductivity. Time delay formula, tau-n, calculates the time delay based on the distance from the source, transmitting antenna, to the scattering point in the tissue and back to the receiving antenna. The time delay helps align the signals for proper image reconstruction. Signal correction equation, SIN, represents the signal processing step where the average value is subtracted from the signal to remove noise or unwanted artifacts. As shown, the signals from each antenna are processed to extract useful information, such as intensity and phase, and these are combined to generate a final image. This process helps visualize the internal permittivity and conductivity properties of the tissue. Image intensity formula, IN, represents the intensity of the reconstructed image. It sums over all antennas after accounting for the time delay, producing the final image with regions corresponding to different tissue properties. This slide comprehensively outlines the process of utilizing prior knowledge to create a region under test, RUT, for investigating internal structures, such as the brain, through the principles of electromagnetic wave scattering. It demonstrates how both physical and electrical parameters are integrated into the system to enable the precise reconstruction of images that can reveal internal tissue characteristics and potential anomalies. At the top left, we see the microwave imaging setup, where multiple antennas are arranged around a human head model. These antennas emit microwave signals that penetrate the head and interact with the tissues inside. As these signals propagate through the head, they are scattered by different tissue types, and the antennas capture the scattered waves from various angles. The positioning of the antennas ensures that the entire region of interest within the head is covered, providing a rich dataset of signals. The central coordinate system, marked on the head model, defines the axes along which the signals propagate and the locations where measurements are taken. This setup allows the system to measure how electromagnetic waves interact with different tissues, producing what is known as scattering parameters or S-parameters. The graph labeled measured signals at the bottom left illustrates how these scattering parameters vary over a range of frequencies. Each curve in the graph represents the transmission coefficient between two antennas, indicating how much of the transmitted signal was scattered or absorbed by the tissues at different frequencies. This information is critical, as it reflects the electromagnetic response of the brain tissues, helping to differentiate between various tissue types or detect abnormalities. These measured signals form the foundation of the image reconstruction process, as they capture the interaction of microwaves with internal structures. Next, we focus on the physical and electrical parameters that are essential for constructing the imaging space. The physical parameters include the 3D focal points where the signals converge, the radius of the region being imaged, the resolution of the system, and the number and location of antennas. These parameters define the geometry of the imaging space and the precision with which it can capture details. On the electrical side, parameters such as the frequency range, the scattering and reflection coefficients, and the channel numbers and positions, whether monostatic or multistatic, are crucial for mapping the space and extracting meaningful data. Together, these parameters determine how the system interacts with the medium being scanned, in this case, a brain phantom, ensuring that the imaging system can capture accurate and detailed information. Moving to the right side of the slide, we see a representation of the sensor points arranged around the investigation domain. These sensors capture the scattered waves as they propagate through or reflect off the tissues inside the region of interest. The scattered waves contain information about the internal composition of the brain, as different tissues scatter electromagnetic waves in distinct ways. The goal of the imaging process is to gather this scattering information and use it to reconstruct an image of the internal structures. The diagram at the bottom right shows the focal points within the region of interest, which are essential for the confocal microwave imaging technique. These focal points represent specific locations where the electromagnetic signals from different sensors converge, allowing for a detailed analysis of the tissues at those points. Before the confocal algorithm is applied, it is crucial to determine the effective permittivity of the region being scanned. Permittivity describes how an electromagnetic field interacts with the material, and selecting the correct value is vital for accurate image reconstruction. By optimizing the permittivity, the system can more precisely map the interaction between the microwaves and the tissues, leading to better imaging results. In summary, this slide visually and technically demonstrates the entire process of region creation and imaging based on prior knowledge. The measured scattering parameters from the antennas, combined with the physical and electrical properties of the imaging setup, form the foundation for constructing the region under test. This step is crucial for solving the inverse problem in later stages of image reconstruction, where the scattered data will be processed to produce high-resolution images of internal structures like the brain. Through this detailed and methodical approach, the imaging system can accurately identify tissue anomalies, such as targets, making it a valuable tool in non-invasive diagnostics. This slide is an overview of advanced methods in microwave imaging, focusing on two major areas: boundary estimation and effective permittivity estimation. It presents the underlying principles, equations, and visual representations related to each concept, helping explain how electromagnetic waves are used to image and analyze tissues. For boundary estimation on the left, the slide introduces two key formulas for estimating boundaries within the head using microwave imaging techniques. Time delay formula calculates the total time delay for electromagnetic waves to travel through multiple layers of tissue. Each layer has a thickness, d, and a relative permittivity, epsilon I. The time delay depends on the speed of the waves through each layer, which is influenced by the permittivity. The longer the delay, the deeper or more resistive the tissue, giving us clues about where tissue boundaries might exist. Reflection coefficient formula expresses the reflection coefficient gamma, which quantifies the proportion of the electromagnetic wave that is reflected when the wave encounters a boundary between two tissues with different permittivity values. Larger differences in permittivity between adjacent layers cause stronger reflections, signaling the presence of a boundary. In the center of the slide, there are two images visualizing the boundary estimation process. The first diagram, head boundary estimation using scattering signals, shows how electromagnetic signals emitted by antennas around the head are reflected from boundaries. These signals provide data to detect the location of the boundaries within the head, e.g., skin, skull, brain matter. The second diagram, confocal microwave imaging, demonstrates the layering of tissues in the head, including skin, skull, and brain, with detected boundaries highlighted. This process relies on the delay-and-sum algorithm to aggregate signals and detect sharp changes in permittivity across the layers. The bottom half of the slide focuses on how effective permittivity is estimated to better understand the internal properties of the tissues. Effective permittivity formula estimates the effective permittivity epsilon EFF at a given point inside the head, accounting for the distance r from the boundary and the overall radius a to the center. The maximum permittivity epsilon max and the constant alpha represent how the permittivity gradually changes as the signal travels deeper into the head. Averaging permittivity over angles averages the permittivity values over multiple angles phi I, which improves the accuracy of imaging by capturing permittivity changes from different perspectives around the head. Visual aids in this section further illustrate how effective permittivity is computed. The image of tissue layers, skin, fat, muscle, inner tissues, shows the electromagnetic wave propagation paths and how the waves interact with different tissues. The scattering data collected by the receivers helps calculate the effective permittivity at different layers. The graph on the right, permittivity versus depth for different entry angles, displays how permittivity changes with depth for different angles: 0 degrees, 90 degrees, 180 degrees, 270 degrees. This demonstrates how permittivity decreases as the waves penetrate deeper, which is critical for reconstructing an accurate image of the internal tissue structure. In summary, this slide explains how boundary estimation and permittivity estimation are combined to enhance microwave imaging, allowing for better detection of tissue boundaries and more accurate reconstruction of internal head structures based on the varying permittivity of different layers. In microwave brain imaging systems, understanding and calculating time delays is essential for creating accurate images of the brain's internal structures. The time delay refers to the duration that electromagnetic waves, transmitted from an antenna, take to travel through different tissue layers, reflect off abnormalities like targets, and return to the receiving antenna. This process hinges on the electromagnetic scattering mechanisms within the body, which are affected by tissue properties like permittivity and conductivity. As microwaves propagate through the brain, they encounter various boundaries such as skin, skull, and brain tissue. These boundaries produce different types of wave responses. Specular reflections occur at the surface of tissues, where the waves bounce off at the same angle as they hit. Creeping wave resonant responses arise when the waves wrap around small objects like targets, which have unique resonant properties that differ from surrounding tissues. The time delays associated with these responses provide critical information for distinguishing between different tissues and abnormalities. The monostatic time delay, when the same antenna transmits and receives, caused by the antenna's physical characteristics tau and the width of the transmitted pulse, tau p. In bistatic channels, where separate antennas are used for transmission and reception, the time delay equation includes an additional term for the distance between the TX and RX antennas. In addition, creeping waves are waves that travel around the surface of an object, such as a target or another scatterer, due to diffraction. These waves are important in imaging systems when the object is smaller than the wavelength of the incident microwave signal. The creeping wave takes a longer, curved path around the object compared to the direct reflection in specular reflection. For creeping waves in a bistatic scenario, the time delay formula would need to account for the additional time the wave spends traveling along the surface of an object, like a tumor, before reaching the receiving antenna. As the waves pass through different layers of tissue, the velocity of the wave changes according to the tissue's permittivity epsilon. The time delay in each medium is the distance through the medium, and Vm is the velocity of the wave in that medium. Since different tissues, skin, skull, brain, have distinct permittivity, the wave speed varies, causing changes in the time delay. The total path delay considers the complete journey of the electromagnetic wave from the transmitting antenna to a focal point in the brain and back to the receiving antenna. This delay is crucial for forming images in microwave imaging systems. In the equation, BI and BJ represent the boundary points along the propagation path, and PF is the focal point inside the brain, where the tumor or other abnormality is located. The refractive indices Nm and Nb and the speed of light are also factored in to calculate how the signal propagates through different layers. Using Fermat's principle, the system identifies the shortest electrical path, which ensures that the microwaves travel the most efficient route between the TX and RX antennas and the focal point. This principle improves the accuracy of the beam-forming process, which combines signals from multiple antennas to create a focused image of the brain. In the right bottom side, the two graphs at the bottom right illustrate how a microwave signal evolves as it interacts with different media and the target. These graphs show the signal's behavior as it propagates through the medium, reflects off the target, and returns to the receiver. In the left graph, the first notable feature is the early time response, ETR. This part of the signal occurs early in time, representing the initial reflection from the target. ETR is critical as it typically provides the most direct information about the target's location and surface properties. It indicates the earliest wave reflections, which arrive at the receiver soon after transmission. In imaging systems, ATR is crucial because it corresponds to the first encounter of the signal with the target, making it the most accurate representation of the target's position and surface structure. LTR represents the tail end of the received signal, typically consisting of secondary reflections or waves that have traveled through more complex paths, such as multiple scattering events or deeper layers within the target. These later signals may carry valuable information about the internal structure or the material properties of the target, but they are often more attenuated and harder to interpret. LTR can also include effects from the surrounding medium, such as waves creeping along surfaces or resonating inside cavities. The right graph further expands on the complexities of signal behavior, focusing on specific peaks and regions within the signal that help to interpret different phenomena. One key feature is the skin effect, which represents the attenuation and broadening of the signal as it passes through a lossy medium, such as biological tissues or a conductive material. The skin effect results in a decrease in signal amplitude, causing the wave to spread out over time. In the graph, this effect is seen as a gradual decrease in the signal strength after the initial peak. The skin effect can also introduce delays and reduce the sharpness of the reflection, making it harder to pinpoint the target. Another critical region is the occurrence of clutters in the signal. These are unwanted reflections from surrounding objects, noise, or equipment, which create additional, often smaller peaks that do not correspond to the actual target. Clutter can complicate signal interpretation, as they may overlap or obscure the primary signal from the target, potentially reducing the imaging system's accuracy. In the graph, clutter signals appear as small, irregular oscillations after the main reflection. Proper signal processing techniques are needed to filter out these clutters to focus on the target signal. Finally, the target reflection is the most critical peak in the signal. This distinct peak represents the actual desired reflection from the target. It occurs at a specific time, corresponding to the moment when the transmitted microwave signal reaches the target, reflects, and returns to the receiver. The time delay associated with this peak provides essential information about the target's distance from the system, while the amplitude of the peak reflects the strength of the reflection, which can be used to infer the material properties of the target. A clear and strong target signal is necessary for accurate imaging, and the position of this peak is crucial for determining the target's exact location. In summary, these two graphs demonstrate the complex interplay between early and late signal responses, signal attenuation due to the skin effect, and the challenges posed by clutter. The target reflection remains the most significant feature, and accurately isolating this peak from the rest of the signal is key to successful microwave imaging. Through careful analysis of the ETR, LTR, and signal peaks, an imaging system can construct a detailed representation of the target, even in the presence of noise and multiple wave interactions. This slide presents a detailed overview of advanced artifact removal algorithms used in microwave imaging techniques, specifically focusing on calibration-based artifact suppression to enhance brain imaging accuracy. These methods are critical in non-invasive diagnostics, as they help ensure that reflections and artifacts, such as skin clutter or environmental noise, do not interfere with the imaging of deeper brain tissues. By implementing these techniques, medical professionals can identify tissue anomalies, such as tumors or abnormalities, more accurately. The slide divides artifact removal techniques into two broad categories: data-independent filtering and adaptive filtering. Both approaches aim to minimize unwanted reflections and noise, thereby enhancing the quality of the reconstructed image and improving diagnostic capabilities. In the data-independent section, several specific methods are demonstrated, each aiming to suppress clutter without relying on real-time data adjustments. The ideal differential subtraction method subtracts a reference head model signal, BR, from the current brain scan signal, BI, to remove known artifacts. The difference between the reference and real-time scans eliminates the constant skin layer effect, revealing deeper tissue structures more clearly. In average subtraction, the skin clutter is reduced by subtracting the average value of the received signals, removing repetitive patterns across multiple measurements. The rotation subtraction technique uses a rotating platform to collect signals from multiple angles. By comparing the signal BR from different rotational positions, artifacts can be minimized. The subtraction of signals at various rotational points helps isolate the brain tissue signal from clutter. The adaptive filtering section focuses on real-time adjustments to optimize clutter and noise suppression. The Wiener filter adapts its parameters to minimize the mean square error between the received signal and the desired target signal. It uses surrounding signal information, BPNN, and minimizes the error through optimization of the filter coefficients, Q. This method is highly effective at filtering out noise and unwanted signals dynamically. The entropy-based time window method suppresses clutter by analyzing the entropy of the signal over time. When the entropy exceeds a certain threshold, clutter is removed by applying a windowing function that zeroes out high-entropy segments of the signal. The entropy function measures the randomness in the signal and helps identify parts of the signal dominated by noise or clutter, allowing for more precise imaging. Let's dive into the four architectures depicted in this slide, all designed for qualitative electromagnetic brain imaging. Beamforming is a crucial technique used in qualitative electromagnetic imaging to focus signals from multiple antennas to a specific point in space. In the context of qualitative electromagnetic imaging like confocal imaging, the process can be broken down into several key steps, each serving an important role in forming a clear image of the target, such as in brain imaging or other complex tissues. The key aspect across all these beamformers architectures is the spatial and temporal variability of the weights and filters, allowing for enhanced adaptability and precision in processing the measured scattering parameters, S parameters. This variability is crucial for capturing accurate and high-resolution images of the brain. Delay and sum beamformer is the simplest beamforming method. In this architecture, signals, S parameters, received by multiple antennas are aligned using time delays. These delays ensure that signals from a particular direction or region of interest are in phase, and then they are summed to create a focused signal. The time delays are applied spatially depending on the target region, and these can change over time if the region of interest changes dynamically. However, this architecture lacks the complexity and fine control of more advanced methods. Ideal for imaging larger structures or areas with relatively stable conditions, but it has limited precision in detecting smaller or more subtle abnormalities. Group Focus FIR beamformer architecture enhances the basic delay and sum method by applying finite impulse response (FIR) filters to the signals. The filters help control the focus across groups of signals, improving the system's ability to focus on specific regions. The FIR filters and beamforming weights vary spatially to target different groups of regions within the brain. Temporally, the filters can adapt to shifting focus areas or changing conditions, such as moving blood or tissue. Useful for improving spatial resolution and focusing on specific groups of tissue. It allows the imaging system to handle more complex scenarios than delay and sum. Dynamic Focus FIR beamformer architecture introduces dynamic focusing, where both the time delays and FIR filters are continuously adapted in real time. This dynamic focus enables the system to track changes in the brain structure or activity, such as moving tissue or active regions. The system dynamically adjusts both the spatial focus and the FIR filters over time, providing real-time adaptability. As brain structures change or activities occur, the system recalibrates to maintain optimal focus. Ideal for real-time applications, such as monitoring during brain surgery or observing dynamic physiological processes. It offers superior flexibility and precision in capturing real-time changes. Spatial Matched Filter Beamformer method uses matched filters to align with the expected signal patterns from specific regions of the brain, maximizing sensitivity to specific targets. Matched filters are designed based on known characteristics of the tissue or anomalies, such as tumors or lesions. The matched filters are both spatially and temporally variant, as they need to adapt to the specific locations and conditions being imaged. The filters can change over time if the target signal characteristics evolve or if the focus shifts. Extremely useful for detecting subtle abnormalities, such as small tumors or lesions, by enhancing the system's sensitivity to these specific regions. It is particularly valuable in diagnostic settings where high precision is required. Spatial Matched Filter maximizes sensitivity to specific brain structures or anomalies, providing the highest precision for diagnostic imaging. This slide presents a comprehensive demonstration of the impact of different steps such as clutter suppression, time delay arrangements, and advanced beamforming techniques for the reconstruction of brain tissue images. Starting with the graph in the top left, we see amplitude versus time plots that display the evolution of signals over time, measured in nanoseconds. Multiple signals, represented by different colors, likely correspond to data from various sensors or antenna positions in a multi-static radar system, where multiple transmitters and receivers are used. The purpose of this graph is to demonstrate how artifacts can be removed from the signals to improve image clarity. It contains time domain signals with and without artifact removal. The signals are displayed in different colors, red, blue, green, showing how the waveforms change after processing. Initially, the signals contain noise or unwanted reflections, which make it difficult to isolate the object of interest. However, after applying the artifact removal techniques, the signals are cleaner, and the object's response is more prominent. This section emphasizes the importance of artifact removal in achieving clearer, more accurate signals that can be used for reliable imaging and detection. In the bottom left corner, two images are shown side by side, comparing results with and without artifact removal. The left image, without artifact removal, shows significant noise or clutter, which obscures the object or target that the system is trying to detect. This could represent an object such as a tumor in a medical imaging system, where the signal reflections from surrounding tissues introduce unwanted artifacts. On the right, after artifact removal, the image is much cleaner, with the object clearly visible. This visual contrast demonstrates the effectiveness of artifact removal techniques, which are designed to clean up the image by filtering out unwanted signals and focusing on the reflections directly associated with the target. In the top right section, the diagram illustrates a process where signals are time-shifted and then summed. The top part of the diagram shows the geometric relationship between the antennas and the object being imaged, highlighting how different antennas receive signals at different times due to varying distances. Each received signal is individually time-shifted to account for these propagation delays, ensuring that the signals align properly when they are summed. This summation is key to enhancing the signals related to the object of interest while reducing background noise or clutter, thus improving the overall image quality. In the bottom right corner, we see a workflow diagram that details the steps involved in improving the image quality through artifact removal. The process begins with hybrid artifact removal, a combination of different techniques aimed at eliminating unwanted signals. This is followed by multistatic artifact removal, where artifacts are removed in a system that uses multiple transmitters and receivers. Additionally, monostatic imaging, where a single antenna acts as both the transmitter and receiver, is included in the process. Finally, the workflow converges in the combined multistatic and monostatic imaging (CMM) approach, where both techniques are utilized together to enhance the final image. The images shown to the right of this workflow demonstrate the success of these methods, with improved clarity and resolution in the final image. Overall, the slide presents a complete workflow for improving signal and image quality in a radar or microwave imaging system. By comparing raw signals and images before and after artifact removal, it highlights the critical role that signal processing plays in enhancing the visibility of objects within the scanned medium. Techniques such as beamforming, hybrid artifact removal, and combined multistatic and monostatic imaging are essential for reducing noise and clutter, ensuring that the final images are as clear and accurate as possible. After time aligning the signals from multiple antennas, the signals are summed together to enhance the signal coming from the desired location, which is known as focusing algorithm of coherent integration. The goal is to enhance the response from the desired location and suppress noise and interference from other areas. The process essentially reinforces signals that come from the focal point, leading to a clearer image. In this slide, we compare 6 imaging algorithms used for breast cancer detection, each visualized with its respective performance. Let's walk through them, focusing on the key differences in resolution, noise suppression, and interference rejection, while also introducing the core mathematical formulations behind each method. First, we have adaptive microwave imaging, MAMI, which is the most advanced method shown here. MAMI operates in 2 stages, using a robust Capon beamforming approach. The intensity which demonstrated by E is calculated by summing the backscattered energy, weighted to reduce noise and interference. You can see the clear detection of the target with high resolution and minimal noise. Its formula is displayed in the right hand, where W is the adaptive weight vector. MAMI's precision stands out, offering excellent clarity with almost no clutter around the target. Next, the multistatic delay and sum (DAS) method extends the concept by using multiple antennas for signal acquisition. It performs slightly better than the monostatic version but still suffers from significant noise and interference, resulting in poor target localization. The intensity is demonstrated by I moving to the robust Capon beamforming (RCB) method. This technique aims to minimize interference while maintaining signal fidelity by optimizing the weight vector. Its intensity formula is IRCB, where R is the covariance matrix and H are the steering vector. RCB provides a high-resolution image, but shows some background interference, though still effective at localizing the target. The amplitude and phase estimation (APES) method focuses on both amplitude and phase recovery of the backscattered signals, offering higher resolution. However, its sensitivity to noise can reduce the quality of the output. The intensity formula is I-APES. APES performs similarly to RCB, but with slightly more noise, though it still achieves high-resolution imaging. In contrast, monostatic delay and sum is a simpler approach that sums signals after time shifting to align them. In its formula, tau I is the time delay. As shown, monostatic DAS struggles with heavy noise and low resolution, making it hard to distinguish the target clearly. Lastly, we have microwave imaging spacetime (MIST), which applies spacetime beamforming to process signals. While it offers some interference suppression, it results in lower resolution and higher clutter compared to the adaptive methods. The intensity formula here is I-MIST, with W representing the weight vector and Xi the received signal. As you can see, the MIST method provides the least clear image, with significant clutter making target detection more challenging. In summary, MAMI and RCB stand out for their high-resolution images and excellent noise suppression, making them the preferred choices for microwave imaging. On the other hand, the simpler DAS methods, despite their computational ease, struggle with interference and poor resolution. APES offers competitive resolution but remains sensitive to noise, while MIST shows its limitations with low clarity and higher interference. Each method presents trade-offs, but overall, MAMI provides the best results in target detection.